Now, there are special cases for bounding phase, and there are two cases that I want to discuss that that is important to know from a technical point of view, but most of the times you do not encounter them in most of the practical problems, right? So what happens if you have a problem like this? If your function is like this, which is a step function, and right, and you sample 3 points on the lower one, right? You will see that at these 3 values, all the 3 cases, the case 1, right, where all the 3 cases that we discussed previously is valid, right, because all the 3 sample values are equal. Fx1 is equal to fx2 is equal to fx3. So all the 3 criteria or all the 3 conditions that we discussed are going to be true in this case, and in this case you cannot do the overall bounding algorithm will get stuck. But again, this is a theoretical exercise, conceptual thing. Typically you will not get such a function. Most of the function will have something other than this, but there might be a possibility that you might end up of having all the same function values for all the 3 points, right? In that case you're stuck. You don't know which case to take, 1, 2 or 3, so your algorithm will be stuck. Here is another case which is important to know, where you might have 2 points here and the third point lies exactly on the optimal solution, right? If that is the case, then you will see the right, according to this algorithm, you need to move to the right, and then you might find a solution here, but then it will take you to move to the left, and then in this case what you will find out, there might be a possibility of basically moving from the left to right and they're not converging at all, right? And that is also a possibility for some class of function, and this is also a special case, right? So in this case, the algorithm will be alternating between the extremes, right? And so it will be moving this forward, this way, and it will never converge on a bounding algorithm. So it's not stuck, it will be keep moving, but it is basically alternating between the interval bounds that is out there, okay? So these are special cases that you should be aware of, but typically these are not encountered most of the times, and you should not worry too much about these cases, okay? So with that, let's move on to another bounding algorithm. So this is the algorithm 2 that we are going to learn in today's class, and this one is known as Fibonacci sequence based bounding algorithm, okay? And this is slightly different than the Swan's algorithm that is done. So Swan's is one, but there are other algorithms that can also be used for bounding, and the Fibonacci sequence is one of them algorithm. So this is algorithm 2 for bounding phase, which is known as Fibonacci sequence. So let's see how this works, okay? It is a different methods which is based upon the Fibonacci sequence. I want to quickly recap the idea behind the Fibonacci sequence that you have. Essentially you have, so you start with 2 numbers, like for example 1 and 1, and then you add them and that results in 2. Then you take 2 and 1, you add them, that results in 3. Then you take 2 and 3, you add them, results in 5. And that essentially is encapsulated by this sequence formula, where Fn is equal to Fn minus 1 plus Fn by. So the numbers in the sequences are generated by this sequence that is out there. Now it turns out that when you take the ratio of nth number and divide that by n minus 1, and as your n is tending towards infinity, this ratio approaches to this value, right? This value right here, 1.618, okay? And this is known as, basically the Fibonacci sequence ratio for Fn divided by Fn minus 1. And this value is essentially used in the overall algorithm for bounding purposes that we have, and that's where the name for this algorithm comes into picture, okay? So again, why it's important to know this? Because typically the initial bracketing that you see with the Swan's method, the Fibonacci method is a faster, and it does a rapid initial bracketing, at least the initial portion of it, right? And so that it might be in some cases more faster than the Swan's method that is out there, okay? So let's look into what are the comparison, what are the details different. So if you look into the Swan's method, right, we had a point where we basically, generated the next point with a delta distance and the previous point with the delta distance, and the distance point between the x1 and x2 and x2 and x3 is kept same in the Swan's method, which is not the case for the Fibonacci method. So if your distance between x1 and x2 is delta, typically you will select an x3, right, which is far away from the delta, right? and this value of alpha is greater than 1, and in fact it is actually equal to 1.61, and that's what you select. So this bounding is not the value between x1 and x2, the distance between x1 and x2 is not same as the distance between x2 and x3, and that's the main difference. And this alpha is essentially specified by this Fibonacci sequence. It is in fact 1.61 times. So you increase not only by delta, but you increase it by some multiplication of 1.618, and we will show what that multiplication is, because it is a little bit more than just 1.61. In different iteration this value is going to actually change. Okay. But the key thing is this alpha is not constant and it's not equal to 1. In fact, this is rapidly increasing. So the length, the next iteration, the length is going to keep increasing very, very fast. Okay. So let's see how we can do bounding with a Fibonacci's, sequence-based bounding algorithm.